I took one, but there might be some leftovers. So, so what do I do then? I look at those leftovers. Let's say I had something like this. Let's say I had, I'll just give them different names. Let's say A, B, C, oops. And let's say that they were connected like this. No, let's say that, yeah. Although, maybe I didn't even have it.
But then it has one on.
True, uh-huh. But it might can finish it here to V0, yes. Yeah, everybody has even. Then what? Then here's what you do. What do I do with this loop? I will remove it. And then what happens? When I remove this loop, what happened with the degrees of the remaining members? Still even, because they lost 2 or even number of each of the vertices. It's actually each of them just had 2 because I cannot come back. So when I remove my first circuit, what's left here? I will have now again subgraph which has even degrees, because if some of them were removed from here, they lost maybe little degrees if there were multiple edges. But what can I do now? Does this subgraph have even degrees each, yes or no? Then what can I do? Do the same thing. Remove one graph and then make a circuit. If I'm not done yet, then I keep going. But here's a very important thing. How do you make Euler path out of that? So here's the story. You go through your path. Let's say I start from V2. And I go like this. V2, V3, V0. And then when I come to this other graph that became disconnected when I remove the first part, I have to finish that loop. So I go A, B, C, come back to V0, and then continue my other path. So those paths go like this. Whenever they meet, then you start a path, go around. When you reach that articulation point, then you finish the inside loop, and then you continue back your loop. Because that's where you are not doubling the edges, and you are repeating each of them exactly once. So for example, where would we have one path? Although I think the examples that we have in the homework are fairly simple. Oh, these are Hamiltonian. So here is one example. Does this, we usually call them open and closed letter. So how would you make an Euler path? Of course, you can make it just, this is fairly simple with the trial and error, but...
An Euler path is different than an Euler circuit?
I'll just tell you that in a second, and then we'll take a break. So what about this one? Let's look at the degrees of those. What is the degree of this vertex?
2.
What about this one?
4, 3,
1, 2, 3, 4. 1, 2, 3. What about this one? Does this have an Euler circuit?
Yes.
No, why not? Because there are odd degree vertices. But now we'll relax the condition, and then we'll say the following. All right, can you do the same thing, but without insisting on being a circle, but being a path? That means you are not required to come back to the same point, but you are just required to visit every edge once. So you can start at one point and end at another one. And then what can you say about this theorem? So do you think that, Euler's circuit does not exist, but, so theorem, an Euler path in a connected graph exists if and only if it has zero or two vertices of odd degree. In the first case, we have a circuit. We have a circuit. In the second case, you must start at one odd degree vertex and end at the other one. Do you agree with this theorem? Our reasoning is the same as before. What is the only difference? The only difference is if I'm allowed to start with one point, then that's where you have that one, and then if you revisit it, you always get two in the meanwhile, and then since you are not coming back, that one stays odd. The same thing with the last one. At the end, after two, last visit makes one, so you're allowed to have two odds. Yes? Yes, because as if all the vertices are odd, that's exactly the first case. In the first case, we have a circuit. In the second case, you must start at one odd degree vertex and end at the other one. So here, is there an Euler circuit? No, there is no Euler circuit, but is there an Euler path? Yes or no? Where do you have to start? You have to start one of those points because this degree is 3 and end with B. Okay?
Are there not 4 points of odd degree or 4 vertices of odd degree?
No, because this is 1, 2, 3, 4. This is 1, 2, 3, 4. This is 1, 2. And here there's, or if I add one more dot there, another vertex, then what would happen? The same thing actually. That one would have 4. These would not change, so that one would have 4. Oh, okay. So now here it is. So how would I make that Euler path? I would start from A, and let's see, this is AB, and let's say that this is C and D, E. So generally, you don't need a special skill. As we said here, whenever you finish a cycle, then just see whatever else is left and see where they connect. So here it is. It goes straight forward if you start from A. So go A to C. As I said, you don't have to think that you're going to mess it up because we have algorithm. So from C, what? Can I go to B? Yes, because you know at the end, because B has degree 3, so I can visit it early. Of course, I don't know how good idea is that, but why not? Let me go AC, then I come to B, and I come back to A. So that's my first cycle. Do you see that? So what do I do now? I remove these 3 edges, so who's left? A is still there, E is there, D is here, C is here, B is here. But what's happening? A and B are not connected anymore. What about B and C? B and C are not connected. This is erased. And all that triangle is erased, so I have the following. I have A to E. I have E to C.
E to D and D to C.
Yes, E to D and D to C.
And then A to C. No, sorry.
All right. So what do I do now? Which one? EB. Oh, that's given as well. Good. All right. So what happens now? Again, I have the same odd degree vertices, so I can do the following. I can go A to E. Then I go E to C, C to D, D to E, E to B, and then what? Now B connects with this cycle here, so I'll go here, here, and here, gluing the other cycle. So whenever two cycles meet, my cycles met at B, actually I do the inside cycle, and then I finish the other one outside. So that in that case, you can always do this automatically. This is an algorithm. Yes?
How would you calculate the number of ways in which you could draw this, or the number of paths in which you could draw the bar without repeating an edge?
That's not simple formula. Generally, yes, it depends on number of cycles, or number of partitions, and all that. So I don't think that there is. Oh, you mean particularly this one?
Yes.
Then just, that's fairly easy to exhaust. So what? I would start like this. Are you going to have a cycle of, so what is the order? Yeah, so from A, you can start to go to your first step. You can go from either A to B, then A to C, or A to E. No, first, you need to choose, like all the permutations almost. So generally what? There are 120 permutations, because at the end you have to visit, how many edges? 1, 2, 3, 4, 5, 6, 7. There are 7 edges. So generally you have 7 factorial options, and then some of them are impossible to visit in that order. So generally, you can just do the elimination on this one. But otherwise, I don't think that there is an easy formula. Maybe if you break it into triangles, and take some partitions or something like that. So for example, look if A, B, and C are covered as one triangle, like I did. So there is complicated. All right, so that's generally the formula. So again, here is also if and only if. If you have two odd degree vertices, then you can connect them. You can always connect them, and the construction works the same way as in this case. All right, so that was the story about Euler circuits and Euler paths. So once again, what about Königsberg bridges? Do they have Euler path? If we relax the condition so that we don't have to come back to the same point, the answer is no. Why? Because it has too many odd degree vertices, because all the vertices, all 4 of them are odd degree, so it doesn't even have Euler path. All right, let's take a break. We'll continue at 42. And we'll consider the other case where the goal is not to visit all the edges, to traverse all the edges, but to visit all the vertices. And those are called Hamiltonian paths.